Okay, so to figure out how all of this is going to actually help us, let's
Hello, hello. There we go. Look up. So, we're picking up right where we left off with our calculus from what we were talking about yesterday. We left off on the chain rule, essentially how we are working with the weighted input onto A. Well, not weighted input because this is just our first input, and then how that gets situated with passing to the next intermediary node with whatever weight and bias applied to that, how that gives you your weighted input that functions with it within activation function onto the next node, uh, which gets you the new A1, which then you then use for weight 2, bias 2, which gives you Z2,
value.
which then continues
Next,
on
we
until you get
calculate
your
activate.
final output that's necessary for actually checking the results of your prediction. Um,
Activation 1.
So that left us with the chain rule. We come here. So with the chain rule now in place, I'm focusing on this.
Simply by passing the weighted input into our activation function. We then do the same thing to calculate Z2 and finally A2.
Right.
We can now
As you can see, we're getting that A1 off of the activation function for Z1, which is coming from here to here. You get A1, which becomes the weighted or the, the input for this node, which then interacts with the weight to the next node, with the bias to the next node, creating the new weighted input for node 3, which then again gets passed to the activation function.
evaluate the network by calculating the cost. So we just use the cost function and pass in the output activation value along.
So this is the output activation value, which is really what we can call this. This A0, sorry, this A1 is really that output activation value coming from node 1, right? So then we have our costs, our C is equal to C of the final activation output, which could be also considered, no, it can't be. Kind of. It's your weighted input, and then it's the weighted input for that node, and then whatever activation function is ran onto it becomes your final output to that node, right? So you're saying the cost function is going to give you C, the final output for that node, and then whatever the actual answer is for whether this is receiver or cornerback, right, goes into that Y, that final Y function or value.
With the expected output for the current training sample, or Y for short. Now,
Oh,
if we think back to this horrifyingly inefficient gradient descent code that I wrote, remember what we're trying to speed up is this calculation here of how sensitive the cost is to a change.
right. And remember, what he's talking about there is how you have your gradient descent per se, or you have your graph, right? And as you are working through learning, you want to find these areas here, right? This is zero slope area. If you think about it as a graph, this is a zero slope area, which if you were to find, let's say uh, if you were to look at the derivative of this right here, if we say this function is something like y equals x, obviously not, but let's say it is, and then we find the derivative, and then this is like um, y equals x minus 1 or whatever, right? So within this, where the y, where this equals 0, so 1, so let's say this is 1, right? This is 2, this is 3. So we have 1 here where this equals, where y equals 0 for the derivative is where the slope of x is equal to 0. And that in itself is where we're looking to learn to. So as we're learning on this curve, right, what was happening before is we'll be here, and then we'd learn, and then we'd correct the weights, and we'd keep trying to get to this area, right? We might overshoot it, then realize we have to go back, overshoot it again until we settle somewhere around here. So he's talking about the chain rule now, or the costs, and how this essentially is functioning and trying to either lower or raise the weights and biases in order to get to this single location here. Um, so now we're looking to essentially refactor this function to have it be useful in a way that's, I guess, more all around, more something. We're gonna see. So let's take a look.
change in any particular weight or bias parameter. So let's say we want to calculate that value for weight number 2 over here. Instead of approximating it, we've seen recently that we can actually get a
All
more
right.
efficient answer.
So we're saying we want to find the value, the weight. Okay. We want to find the value here for weight 2 that gets us closer, from my understanding, right? Gets us closer to the proper output, right?
By calculating the derivative. And I'll write this with these fancy curly d's since we're dealing with functions with multiple variables now. Anyway, this might look a bit confusing to calculate because we're trying to figure out how W2 affects the cost, but it isn't one of the cost function's
Yeah.
inputs.
So we're looking at how W2 affects cost because the way we change the weight is what's going to change our output towards the final activation value or input weight to the next node that doesn't exist, essentially.
So, to unravel this mystery, there's one final calculus concept for us to contemplate today:
Yeah,
the chain rule.
here we are.
The chain rule tells us to simply look
Chain.
at how W2 affects Z2, which we can write out like this, and then look at how Z2 affects A2, which I'll write out over here as well.
Okay, okay. So how Z2 affects W2, now A2 affects Z2.
And finally, look at how A2 affects the cost, which once again I'll write out over here.
Okay, so here's my interpretation of it is if there is a variable in a function and the result of that function is used in another function and the result of that function is used in another function, then you could figure out how that first value relates to each and every one. That's how I'm viewing it, right?
All we need to do now, according to the rule, is multiply these partial derivatives together, and it will give us the result.
Right? So we're saying, in my opinion, right, I have y equals mx plus b, right? And then I have z equals a um, y, and then I have, we can say w equals z squared, right? If this makes sense, I don't know. And what I'm looking at here though is kind of the same pattern of I want to figure out how x affects y, which affects z, which affects w, right? So that I can find the w over x, right? Because we're saying c over w, c over w, have w over x. So we're saying w over x equals, um, you're starting from the top and you're saying, well, x, y, right? And then the final is the first. So you're saying y, x, And you're saying times, um, I would say A, no, ZA, right? Yeah, it'll be ZA, Z over A times, and then it'll be the final again, W over Z, because it's in here. So then you multiply all these, which is going to, hold on, should it be ZY? Oh, this is a, yeah, it should be a Y, right? Because now you're saying we're multiplying this crosses with that, that crosses with that, and you get W over X equals W over X. Great.
Affects the cost, which
Let's
once
see
again
here.
I'll write out over here.
So what does that
What
do
we need
for
to do
us?
now, according to the rule, is multiply these partial derivatives together, and it will give us the result we're looking for.
Uh-huh.
We can even kind of see that this is true, because if we think about how fractions cancel out when you multiply them, this gives us the correct result. So, our task now is figuring out what each of these partial derivatives actually is. And let's start with this one on the end.
I see.
Here's our code again for calculating the cost of a single node.
Okay. So this is our code for calculating the cost of a single node. A minus Y. So the activation output, right? This is the activation output value. And then this Y is the expected output, right? So whether it's 1 or 0 or 1, I assume. And then squared. So let's do the math behind that, which, I mean, we definitely got a nice refresher on. Long story short, you're looking at a minus y squared, which then ends up being a minus y, which ends up being a squared first outside, so positive ay, because you're, in my opinion, it's, I mean, wait, wait. First outside, sorry, this is negative. Let's, can I, yeah, whatever. All right, so you have a minus y squared, which turns into a minus y, a minus y, which gives you a squared, and then outside minus ya, inside minus ya, and then last plus y squared. And then, so you're saying a squared minus 2ya plus y squared. And then that's all you can really do with it, right? From my opinion.
And we need to figure out the partial derivative of this with respect to the output activation value. Here's our code again for calculating the cost of a single node, and we need to figure out the partial derivative of this with respect to the output activation value.
Hold on. So partial derivatives are used when dealing with functions with multiple variables. For example, C a y has two parts to the derivative that we could calculate. C a tells us how the cost changes if we make a tiny change to a but keep y the same. Okay, so from so this in a way are two different functions, yeah, because you're saying CA and CY. So then that's why you have to do the partial, the derivative of this and derivative of that. There's two variables inside.
Shortcuts for doing this sort of thing, thankfully, but I'd just like to quickly show how the approach we used earlier still works exactly the same way for a multivariable function like this one.
Okay.
So over here, which we used earlier still works exactly the same way for a multivariable function like this one. So over here, we're looking at how the cost changes in response to a tiny change to this output activation value.
Ah, I see. So he's treating a y as x. I see. So this is really this. But then since you're focused on the 2, so then it becomes CA plus, um, so this would be C plus CX plus H normally, but now we're saying CA plus H, comma Y. I don't know what the comma Y is doing necessarily though. A, right, this would be X normally, comma Y over that same change at H. What is, let's try to figure that out real quick. What exactly is this? Why is it AY? What's the mathematical understanding behind that? Then doing um C, what was it? A plus AHY minus C of A Y divided by H. C is a function that depends on two inputs. Very thank you. That's very programmy, right? Obviously. So we're saying the same way, you have um, a print function printing x, y, and then this could be like print x, print y. So we have a function that's taking two inputs, right? Even though it's not math, it's still same concept. Okay. So think of it like a machine with two knobs. So you have a machine, and you have knob one, knob two, A, this is Y. Turn either knob, output changes. That is correct, right? So one knob machine is like this, where you just have X, and this is a two knob machine, nothing deeper than that. When you take a derivative, you only move one knob at a time. So if I nudge a tiny bit while keeping Y frozen, where does C change? How does C change? That's called a partial derivative. But in formulae, so I'm saying in this formula where two things are changing, I'm going to just change one thing to see what happens. Derivative of C with respect to A, although there should also be a derivative of C with respect to Y, if that's the case, right? Because eventually we'll need to move Y, and I wonder if that'll be essentially C A Y plus H minus C A Y divided by H. You might need to do this as well, right? You only have one knob, so there's no ambiguity. But okay, but at the end of the day, why would you change Y when this is the final output? This deciding factor, right? This is telling me if it's a receiver or a cornerback, right? So there's nothing to change there, essentially, in my opinion. Could be wrong. So we're here. Pretend Y is just a number sitting there, which it is, because we're saying that is your output, your desired output value, right? So 2a derivative is 2a. Derivative is 0 because y is frozen. Uh, now freeze a, do the same. Oh no, you do the same. Okay, so you do the same. Ah, back propagation. We're gonna look at that very soon. Cost equals loss. many knobs. If I change this one parameter holding all this fixed, how does the loss change? Okay, so what I'm understanding is, and we'll see if I'm wrong later, is you have your parameters of your forward lean, you have your parameters of your foot separation, right? You have your parameter of cleats being used, possibly. I don't know, right? Whatever your parameters are, you're now saying, well, if I change this weight, the weight of the forward lean to be higher, what happens, right? If I weigh the weight of my foot separation to be higher, what happens? Cleat, what happens? And then after finding that out, I can properly now say, okay, I need to raise this, lower this, and now I'm 90% right instead of 60% right. So this weight scheme is now my preferred weight scheme. Is how I'm assuming this is gonna go in the future, right? A derivative means changing one input while freezing the rest. Okay. All right.
And we're then dividing by the size of
So here we're taking one input,
that
freezing the
change.
rest. Oh, because if you okay, okay, hold on. Let's talk about it. Because if we remember directly, it was like that before. The picture that we used to work with is more like this. Or oh no. We were working with two. Okay. Hold on, we might be onto something. It was like this, and then this, this, and then this, right? And then this was receiver, this was cornerback, right? And then this is, let's say, forward lean. This is foot separation. And this went here, and all that connected to here. But also, this went here, this went here, all that connected to there. Also, this went here, this went here, all that connected to same vein. This connects to here, this connects to here, this connects to here. So let's say we're here. This technically has two inputs coming. So in other words, I would assume the cost would be like A, B, Y, right? So then now I could understand, okay, if I mess with the weight here of this A with forward lean, how close do we get to Y? Or B, same thing, same situation, whatever the case may be, you can now work with all these different inputs. So here we might be, the cost of A, B, C. Oh, sorry, Y as well. Should be right there. So A, B, C, Y, A, B, C, and then the output value, the expected output value to be at the end of the day, right?
Like before, let's write this out in full and expand everything, which is pretty tedious, but we then get to cancel a bunch of stuff out, which is always satisfying. I'll tidy that up, and we can see once again we end up being able to cancel out this division by h, which
Mhm.
is crucial to the final step of then being able to say that as h approaches 0, this is going to approach simply 2 times the output activation minus the expected output. So
Mhm.
there's our answer, and in code that would just look like this. Okay, so we've
So
activation.
you're saying two because okay. So we figured all this out. We started with this. Why did we start with a minus y squared though? Right? Why did we start with that? That was our cost function. So how do we find the cost function to begin with? What's the why? Yeah. It's just a single number that's the answers. How wrong am I? Small number is good, big number is bad, right? So if you system can't answer how wrong, it can't prove. Okay, I agree. What must they call once and compare? What you predicted what actually happened. Yes, the output activation function, which is what we consider to be, which, as far as his thing goes, he's calling, his A0. Why? I guess we should really say like, let's just say A8, right? And this is after one, two, three, four, five, 6, 7 nodes. The output here, after all these layers, these convolution layers, the output here is either going to be um, your receiver number or your cornerback, right? And then Y itself, this is going to be A8, and then Y itself is either, let's say, is wide receiver, right? So a small number is good. So let's say I say the final value here is like 1.12. And then receiver for Y though is 1. If I subtract that, then we're getting 0.12, which is to me a small number. But let's say I choose cornerback, which is 2 maybe. So now I'm subtracting 2 by, no, say I say it's 2 and cornerback's 0 maybe. And now the number's 2. This might be considered a big number. Maybe. We'll see. Truth is 5, predictions 3. You're very wrong. You get the absolute, and then oh, okay. So that's why okay. So really, I see. So you're really just subtracting, right? But then you're saying you want the absolute error in case it's negative. But then you also are punishing more the bigger the number is because you're squaring. So I mean, two squared is 4, but once you get to like 5, now it's 25. So the number becomes huge, even though you're only 3 points off. So turn one mistake into a cost function. So this in itself is probably just your general cost function for everything. Okay. So we have a cost function.
Which we used earlier, it still works exactly.
Okay. The cost equals your final output for that node minus what your prediction should have been, or the truth value squared is a good cost function to always use. Oh, wow. A is a real number, not a probability, not a class label. Errors are symmetric, being high or low is equally bad. Large mistakes should be punished more. Okay. Ah, I see. I see. So I should be able to look at a joint angle, which is going to be important to what I'm trying to do, right? Look at the joint angle, and I need to say this picture is 30 degrees, right? But if they say, no, it's 40 degrees, right? Or 25 degrees, right? That needs to get boom, 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 subtracted, essentially absolute value and amplified. You get the good cost. Now, if it's cat versus dog, right? So receiver versus cornerback, really, this is what I'm going to need. So doesn't deal with confidence, gradient Spanish too early. So I'm going to be working with cost cross entropy, right? So what is the cross entropy function? It was the log stuff. That's what it was. Okay. So, but either way, it's still the same understanding that you're saying you get a cost function, you get a value, and then you do something with that value to change the weights. All right. How do we update the weights after receiving the cost value? Uh-huh. What derivative do we actually compute? For each weight, W, C, you get the cost, and how sensitive is the cost to this weight? Large value. So you find a derivative for each weight, and then you can understand how sensitive the cost is to that specific weight. So this weight here, we would find the derivative here by finding the cost of either this guy or this guy. I want to say it's this guy though. And then depending on the value, we'll figure out how much the weight matters, and then we can work from there. All right. Back propagation, we're not there yet, so let's keep
Okay,
going.
the same way for a multivariable function like this one. So over here, we're looking at how the cost changes in response to a tiny change to this output activation value,
Uh-huh.
and we're then dividing by the size of that change. Like before, let's write this out in full and expand everything, which is pretty tedious, but we then get to cancel a bunch of stuff out, which is always satisfying. I'll tidy that up, and we can see once again we end up being able to cancel out this division by h, which is crucial to the final step of then being able to say that as h approaches 0, this is going to approach simply 2 times the output activation minus the expected output. So there's our answer, and in code that would just look like this. Okay, so we figured that one out. Next, let's look at how the activation changes in response to the weighted input. So here's that sigmoid activation function we're currently using,
Mhm.
and calculating its derivative is quite a bit more involved than the others, so I'm just going to skip right
And then the activation function is what allowed it to not be so choppy when messing with the weights, and it's more of a smooth, rounded
to the
function.
answer, which turns out to be simply the activation value multiplied by 1 minus the activation value. Let's quickly graph it at least, just for interest's sake, and here's what it looks like.
Uh-huh.
Alright, for this last one, we want to know how the weighted input changes in response to the weight. This one's very easy because if we just look at our equation here, we can see that the amount of effect that a change to the weight will have on the weighted input depends entirely on the input, which is this a value here. For example, if a is 0, then changing the weight would have a 0 effect,
Mhm.
whereas if a is 10, then changing the weight would have a 10 to 1 effect, and so on. So that's our answer. We now know how the cost is
I see. A will amplify or decrease the effect of W.
affected by the second weight. We just need to figure out the same thing for the first weight. So here's the partial derivative we want to calculate, and if we just look at how the first weight ends up affecting the cost, we can again use the chain rule to figure this out.
Jeez.
Taking a closer look, we can see that these two partial derivatives on the end are the exact same as these two, so we know those already.
I don't know.
Then over
Be
here,
right back.
this is the
Alright, where we left off. Taking a look at the chain
The same
rule.
thing as this, just
Mark one the
taking place in a
derivatives and
different
now the
layer.
activation
So
value.
we already know how to calculate it. And it's the same story with this one being the same thing as this, just again in a different layer. So all we need to worry about then is how the weighted input changes in response to the input. But again, if we just look at this equation here, we can see that the amount of effect that a change to the input will have on the weighted input is determined entirely by the value of the weight. So there's our answer. And we now know how the
Working the
cost is
same way
affected
as
by
the
both of the weights
this up
in our
here.
tiny network. Okay, I'm going to tidy these notes up a bit because it's time for our little network to grow up. This does mean that our notes here don't make total sense anymore, but they do translate fairly intuitively, I think, so they're going to guide us as we work through this. Let's begin with this calculation over here, where we're taking the partial derivative of the cost with respect to the activation of our output node, and multiplying it by the derivative of the activation with respect to the weighted input. Of course, we now have two output nodes, and that just means we'll do the same calculation again, but using the activation of this other output node and its weighted input instead. So we end up calculating two separate values, which I'm just going to call our node values, because I'm bad at naming things. So over in the neural network script, I have started working on this little function, which takes in a single data point and runs it through the network. And I modified the layer code slightly so that when that happens, each layer stores all the information we're going to need, like the weighted inputs and so on. After that, it asks the output layer to calculate the node values, which it does just like we talked about. Alright, so we're now ready to figure out how each weight in the final layer is affecting the cost. So that means we'll actually be calculating 6 different values in this example, one for the weight of each of our connections here. To do this, we need to multiply our node values by this partial derivative here, which we figured out earlier was just the activations from the previous layer. How that'll work for this connection, for example, is we'll
because
take
they're
the
being
activation
multiplied
from
in
the
the
previous
function.
layer that's going to be input along the
That
connection,
y equals
and
mx plus b
multiply
function.
it by the node value that it connects to on the other end. And we'll be doing that for all of them. So just as another example, for this connection, we'd be taking the activation coming out of this node and multiplying it by this node value on the other end. So over in the layer script, I've made this update gradients function, which takes in the node values, and then for each connection, it calculates the partial derivative of the cost with respect to the weight of that connection, and then uses that to update the gradient. While we're here, we should actually also be updating the bias gradient. So to figure that out, let's quickly tweak our maths to be with respect to the bias instead. And we can see that we just need to multiply the node values by whatever the partial derivative of the weighted input with respect to the bias is. So let's once again have a look at this equation, and here we can see that there's nothing affecting the bias value, which means that however much the bias changes, the weighted input will change by the same amount. So that partial derivative is just 1, and I'll go ahead and add that to the code quickly.
Derivative costs with respect to the bias.
We'll of course tell the output layer to update its weight and bias gradients using our new function. Okay, so we can now move on to our second equation here, and let's focus on calculating this new set of node values for our hidden layer. As we noticed before, this uses the old node values in its calculation, so we first just need to take those and multiply them by this partial derivative here, which we figured out earlier is the weights between the two layers. So how this works is that the first of the new node values here will be equal to the weight of this connection multiplied by the old node value it connects to.
Again, those are the partial derivatives. These are the weights because a in the function is working with w plus b. So because this is what determines this, then the partial derivative is just w.
Plus the weight of this connection multiplied by the old node value that it connects to will be equal.
All right, let's see.
So them to calculate. Let's head back to the neural network script to finish things up. Those to implement. This implementation a little put it only go backward. It looks like hanging fruit would be making it process all the data points and written did. Okay, the 1 meaning white. Now, I've set up a simple interface for creating our neural network here, so I'll make one with 784 inputs to take in all those pixel values, and 10 outputs for telling us which of the 10 digits it thinks it's looking at. Let's take a moment quickly to wrap our heads
And this we saw so many times prior, right? Convolution layers.
around this. So our fruit data had just two input values, meaning we could draw each data point in two-dimensional space.
Mhm.
For the digits, though, we now have a 784-dimensional input space, which is a bit trickier to imagine. So let's just pretend it's in 3 dimensions instead, with each axis representing the brightness of a single 3 pixel over here, and so on. Images just need which is still dark. We don't actually care about
The min batch size, we already set that up on our own.
sent
It's
animated.
trending.
Great. And
That's
also,
awesome.
test image over the look at it.
This in
So
itself
plain
just seems
internet
like it's kind of,
the training tip that's presumably made. It's definitely done that.
yeah. Okay. I think we came out of this with all the stuff that we needed to really get a good start and fundamental and foundation on what we need to really, really start writing our own out. And I'm extremely excited to be able to come back to all of this and see how much more concretely we can handle the problems that come up. So all in all, this is pretty much it for me as far as the this video goes. We're done with it. We spent a good enough time going through the fundamentals. I mean, it's been 4 days worth, 5 days worth of information, right? So I feel confident, and tomorrow, to me, I want to start getting training done. Let's start actually putting in some of these values, start training our model, and actually doing what we came here for, right? So hope y'all learned something. I had a great time, and I will see you on the next round.